Hello. So this is a lecture, the first lecture on the finite volume method. So the finite volume method can be better explained through the generalized differential equation, the generalized conservation equation. So we have the generalized differential equation, which for any parameter, some parameter phi, can be written as one with a spatial, a temporal, a spatial variation. Sorry. So in this equation, we have this gamma to be the diffusion coefficient, and S is represents the source term. So this equation is for any scalar phi, and this phi can actually be replaced with different values or different scalars to get different conservation forms. So for instance, if I say phi is 1, then what we get is the equation for mass conservation. If I said phi was the velocity or components of velocity, then we can recover the momentum equation. We can also have phi to be, for instance, as the turbulence kinetic energy. And then essentially we have the equation for the turbulence kinetic energy, typically in a two equation model. And we can also have phi to be equal to temperature, and this would lead to the energy equation for solids, liquids, and ideal gases. Now what we'll do is that we'll look at the solution strategies for this generalized differential equation in such a way, or using this key concept of the finite volume method, and we will try and highlight how this method is different from the finite difference method. So as the word suggests, the method is called finite volume. It is essentially based on the control volume concept. And when I say it's based on the control volume concept, there are essentially a few things that a beginner needs to understand about this method. The first is, let's say we have a computational domain in which, let's say we want to calculate maybe the velocity or the temperature distribution. Okay, analytical methods would essentially give you the variation of any property, let's say some scalar phi, as a function of, let's say, x, y. If I can forget about the time dependence, and we can say, let's say this is y and this is x. So that will give you, analytical methods will give you a continuous function. What we are looking for is a discrete analysis. So the fundamental idea here is that we will divide this volume or this domain into non-overlapping control volumes, and each of these non-overlapping control volumes will surround a grid point. So let's say something like that. Okay, so we have these non-overlapping control volumes which surround a unique grid point. So we have non-overlapping control volumes that surround a grid point. Okay, and just to highlight this concept, so we have this becomes one control volume. Right, so this is sort of like a representative CV, and this is our grid point. That is the first idea in the finite volume method, or the first concept. The second thing, the more important part, is that in each of these control, or in each of these volumes, which we now can call as, a smaller, they are not infinitesimally small. So these are sort of finite volumes, volumes of finite size. So in each of these volumes, control volumes, we will integrate the differential equation. So the differential equation will be integrated over each of these control volumes. Now, in doing this analysis, in integrating in each of these smaller volumes, what we'll need to do is to make some assumptions. So I would not go into details of those assumptions right now. We'll come to it at a later point. But it's something that can be specified here, is that what we'll end up assuming, or what we'll end up to assume, is some kind of piecewise profiles, okay, which would express the variation of the scalar phi between these grid points. And this will be done primarily to evaluate the spatial derivatives, and as we'll see later, these will be derivatives that are typically in the diffusion term. So we'll get to that point, and then it will make maybe more sense at maybe in a few minutes from now. Now, the idea of doing these two steps, basically what they will do is that they will lead us to some kind of a discretization equation that will contain values of the parameter phi for a group of grid points, very similar to the way the finite difference method works. Now, the third key concept of the finite volume method, and one of the reasons why it is very popular, is that the solution obtained by this method it has key properties that it implies. So the solution method implies that you have exact integral conservation of quantities such as mass, momentum, energy, etc. for any number of control volumes. So it doesn't matter how many, with reference to this figure, it doesn't matter how many cells we divide the entire volume into. The solution process will satisfy or will give us exact conservation, and so it will obey conservation over each CV, over each control volume. Okay, for and the second thing it will also do is that it will also give us conservation over over the whole calculation domain. That basically follows from the first bullet, from bullet A, because if you get conservation on each volume, then it should also lead to conservation. By summing it up, you basically should get conservation over the entire domain. So key aspect that you need to remember now is that the characteristics are true for any, or the conservation or the solution will be true for any number of grid points, which means even coarse grid solutions that we typically use to get started within the solution process for debugging or for testing, getting some rough idea about variation of scalars over a domain, and even with time, these coarse grid solutions will also exhibit exact integral balance, which is a key point. Okay, and the other aspect that you should remember is that we are looking for solutions. So we're looking for solutions at grid points only. Okay, so we're not looking for variation of solution. We're looking at how this parameter phi, or this property phi varies, and we're probing its values only at grid points. The reason I say this is that we have assumed some profile, as I said in this part, that we would have assumed some profile to evaluate the spatial derivatives. So this profile assumption is no longer important, or can be forgotten. That's a more easier way of saying it. Can be forgotten once the discretization equations are solved. So we don't need to worry about how we, or what we assumed in terms of variation of these properties. What we need to do is look at these variations can be ignored in the end, or can be forgotten in the end. So to get you started, let's look at a very basic example of the finite difference or the finite volume method, and we'll choose the steady 1D heat conduction equation. Okay, so it's 1D, which means that basically we have a domain which is one dimensional. So let's say we have X, okay, with some boundary conditions, and we want to solve for the temperature in this system, and the governing equation is d by dx k dt dx plus some source term is 0. Right, so this S is essentially rate of heat generation, and can have units of watt per meter cube. Okay, so remember this is a general equation. We are going to be solving this equation at different grid points. So the way the process works is that, let's say we are at some general point P, grid point P. So the idea would be to write the discretization equation from the governing equation at this point P. Okay, so just to elaborate further, let's say this is the point P on the domain. Okay, so we divide, as we said, we would divide the entire domain into finite number of volumes, control volumes. So let's say we divide P, and let's say the neighboring points are in typical, the terminology is that you say the left hand neighbor is W, west, the right hand side neighbor is E or east. And when we go to 2D, we'll see that the neighbor to the top will be north, N, the neighbor to the south will be S. Okay, so let's say we divide by into different or into volumes. So let's say this is the volume surrounding point P. This volume has a width of delta x. We typically label the faces by small alphabets. So small w becomes the interface of the control volume to the left. Small e becomes a face to the control volume to the right. When we go to 2D, small n will become the face on the top, and small s will become the face on the south. We can also write the distances between the grid points. So that terminology is based on delta x with a small subscript e, which means the distance on the left, and this would be delta x small w. Okay, and this we assume that of course x is this way. Okay, so these dashed lines, right, these two lines are actually faces of the control volume. Okay, for now their exact locations are not very important. It's not, doesn't mean that they are not important at all, but they're not important for the time being. We'll discuss that in due time. Okay, so what we'll do is, that was the first part. We divide the entire domain into different volumes, right? So basically we have divided it into volumes and so forth and so forth. Okay, now what we'll do is we'll assume a unit thickness in the y and z directions. Okay, and we'll integrate the original governing equation over each of the control volumes. So for now, let's just integrate it over this control volume. So let's integrate d by dx k dt dx into the elemental volume, which will be delta dx into 1 between the west and east faces. Remember, the interfaces or the volume actually is this volume. Okay, so we have to integrate between west and east. Okay, so we have dx plus integral between west and east faces of s, and again elemental volume, which is dx into 1. This is 0. Now the first integral is fairly simple. It's d by dx of k dt dx into dx, which becomes essentially, this will become d of k dt dx between west and east, right? So we can write this is going to be, what we'll get is k dt dx at east face minus k dt dx at the west face plus integral s dx between the west and east faces is 0. Now to go further, this is essentially the integral form of the conservation equation. To go further, we need to assume how temperature, this variable T, would vary in the control volume that we are looking at, so between faces W and E. Okay, so we need to assume how T varies between E and W. So the two simplest options that we have, again these are not the only options, but the two simplest options are, so let's say, and we'll try and do it on the same picture. So let's say we plot temperature here and this coordinate x here. Let's say this is point P, and just for visual clarity, I'll exaggerate. So let's say that point W is here, point E is here, okay, and let's say this is W, small e, okay. So let's say W, at point W the temperature had some value, at point P the temperature had some value, and it's at E it has some other value. Let's say, so even though this is not known beforehand, it could be basically from some physical guidance, or from the last iteration that we have some understanding of how the temperature will vary. Okay, so the two options, the simplest option that we have is we could assume, so as a guideline let me use this. So we could either assume that the temperature that is at point P, remember they would, or at rather at point W or at point P for example, we could assume that the temperature prevails over the entire volume, that it is a representative temperature of the entire volume, sort of like an average value, right? By that concept, what it means is that the temperature in W, at W would prevail in its control volume, and temperature at E would prevail on its control volume, right? So we could assume that the temperature prevails in the entire volume. So this looks like a very good approximation, except then when we do this, this would lead to a situation where the value of dt dx is not defined at the control volume phases, because temperature essentially shows from here to here, it shows a certain jump, and that is not defined. So you cannot calculate dt dx at the boundaries, or at the boundaries of the control volume. The second approximation that we can make, and let me use a different color to do this, is that we could assume some kind of a linear interpolation of temperature between each of the grid points. So if temperature at point W was this, we could assume the temperature varies linearly from W to point P, and then again from point P to point E. By doing so, we now have the slope at the grid volume, at the grid faces, or at the control volume faces, right? So this is this, by this line I mean it's linear interpolation. Again, as I say, these are not the only choices. We could take a quadratic approximation as well. Okay, but there are some difficulties associated there, but that we'll come to at some point later in these lectures. Now this linear interpolation is a preferred form, because this linear interpolation leads to, or the linear interpolation can be easily used to calculate dt dx, and so that makes it the preferred form. So this is the preferred form. Okay, so what we'll do in this series of lectures is to actually look at this linear interpolation as a preferred form for approximating the temperature variation between grid points, to evaluate, again, not for everything, but to evaluate the slope of the temperature function. So I'm looking at evaluation of these numbers. So individually I have now understood what, or I rather have a guess for temperature variation between two grid points. So I can now write k dt dx at the east face. Let's say I could approximate this as ke TE, sorry, TE minus TP by delta XE, right? Where delta XE is essentially this distance, and this is delta X W. And we can also write in a similar way K dt dx at the face W as KW TP minus TW by delta XW. So now what do we have? If I put these approximations into this conservation form of the equation, or into this integral form of the equation, what we'll have is KE TE minus TP by delta XE minus KW TP minus TW by delta XW plus, and what now I'll do is, instead of writing integral S dx between W and E, I could actually say integral S dx is some average value into delta X, because remember the control volume size or has the width of delta X. So I would replace here this by S bar delta X, where S bar, as I said, is the average value of S over the control volume. So now we can rearrange this equation and we get KE. So rearrange would mean just collect like terms together. So KE by delta XE plus KW by delta XW into TP would be KE by delta XE TE plus KW by delta XW TW plus S bar into delta X, and like the more standard form of writing this equation, as you'll see in various textbooks, is AP TP is AE TE plus AW TW plus B, where if I compare, AE is KE by delta XE, AW is K delta by delta XW. Please note that this is a capital W and these are small w's, and AP is AE plus AW, and B, the constant, is S bar delta X. So this becomes the general form or the working form of the equation that we will try and solve. Okay. Now in general, when we go to 2D and 3D analysis, the number of grid points or the number of neighbors will increase, and so the general discretization equation would look like APTP. So this is true for 2D and 3D, to be summation A and B T and B plus B, where NB essentially denotes the neighbor points, right? Because just to give you an idea, in 2D what we'll have is, if there is a point P, right, we can have its neighbor as W, E, and then N and S. So the control volume would be something like this, where this will be the east face, the west face, the north face, and the south face. And so we will be solving the equation in this control volume. Okay, so this brings us to the first key idea or the first form of the discretization equation that we get in the finite volume method. Now, one thing that I've forgotten to mention here, but we'll do it in the next few lectures, is how do we get Kw and Ke. So if the thermal conductivity is a constant, then these will anyway be equal, and this will be a given value. But if conductivity depends on temperature, or if conductivity depends on it's a material which has some heterogeneity, some sharp change in conductivity, then these have to be very carefully chosen, right? So we have to have some method of choosing this. So we'll do this in the next few lectures. Okay, how to address this will be discussed in the coming lectures. Okay, so let me make a few comments here about this method now. Excuse me. So first is that we need not take the simplest possible profile assumption for calculating dtdx. Okay, so we need not take the simplest profile assumption for calculating dtdx. And essentially what I mean to say is that other interpolations are also, or other interpolation methods are also allowed. But ideally, in the limit that the grid spacing becomes very small, all interpolation schemes should actually give you the same answer. Okay, that is a fundamental idea on which we are working, that as we go smaller and smaller in terms of spacing between the grid points, all schemes should actually give you the same physically realizable solution. The other part is that we need not use the same profile. So we use the linear profile for calculating temperature dtdx, but we need not use the same profile for calculating other variables. For instance, for calculating the average value of s bar, and s could actually be depend on temperature itself. It could be a non-linear function of temperature, or it could be a constant. If it's a constant, there is no issue, but then if it depends on temperature, then we would have to do some, break it down into some form where it can be easily integrated. So if for calculating s bar, we need not assume that T varies linearly, okay, between grid points. So these profile assumptions are actually independent. The same thing can be said about K. If I need to calculate Ke from Kp and Ke, and remember that we will only have nodal values available to us. Okay, so the values at the faces of the control volume would not be known. So to calculate Ke from Kp and Ke, we again need not assume, or we can have any other assumption, right? So we can have any assumption and not necessarily linear variation, especially if K is a function of temperature. Okay, the third comment that you should need to keep a close eye on, or give close attention, is that, as I said, for a given variable, the problems in this case, the variable that we were dealing with is actually temperature. So we need not take the same profile assumption. Same profile assumption need not be used for all terms in the equation. What it means is that we have dt dx being evaluated using a linear variation of profile, or using a linear variation of temperature, but we also have temperature. For example, if I look at the advective term, it will actually give me a temperature. A temperature dependence will also show up there. So these two profiles or these two variations need not be evaluated using the same profile. Okay, so there is a freedom of choice. To put it this way, there is a freedom of choice in choosing what or how you want things to vary, or how you expect things to vary, or how you want to simplify your governing equation when you go to the integral form, and from there, from the integral form to the discretized form. Now this freedom of choice is essentially dictated by certain guiding principles. So these guiding principles are the ones that will actually give us or lead us to the correct solution. So the first guiding principle is about obtaining realistic solutions, so realistic behavior, and also achieving overall balance. Okay, so what I mean by these aspects here is that even when we solve the problem for very coarse grid solutions, so when you have coarse grid solutions, we want them to give us a realistic behavior and overall balance. So we want them to have physically realistic behavior and overall balance. What I mean by physically realistic behavior is that, let's say we're dealing with a problem in heat conduction. Okay, so let's say we're dealing with heat conduction with no sources, which basically means that S is 0. Okay, then we know that the temperature at any point in the domain should not lie outside the range dictated by the boundary conditions, right? So if we have some domain and the temperature here is, let's say, I know the temperature, let's say, is here is 0 degrees Celsius, and I say temperature here is 100 degrees Celsius, then I know that at any given point inside this domain, the temperature will always be between 100 and 0, right? So that key aspect will give me, so if I get, so physically realistic behavior would mean the temperature is always in this range. Okay, overall balance basically means that we have to have a scheme or a method by which there is complete balance of fluxes in the control volume, or entering and leaving the control volume. Okay, so we need to take a lot of care in calculating fluxes at the CV phases. so that we have, so that we can ensure, actually, to ensure integral conservation. And we'll look at this point in more detail very soon. So physically realistic behavior and overall balance would essentially give us these two aspects. We'll talk about temperature being bounded, and second would mean that the fluxes have to be carefully chosen so that you have conservation over the entire domain. The second aspect would be about source term. Now let's say the source term S is a function of temperature, some function of temperature. However, the method that we are working out will only allow solution of a linear algebraic equation, right? So we are trying to go to APTP is A and B, T and B plus B, and so this is a linear equation which has to be solved at the end of the day. So we need to somehow find a way of linearizing this relationship. Then only we can actually cast our system into this discretized form. What it means is, when I say linearizing, what it means is that we need to look at expressing S bar as some constant plus a quantity which is basically a coefficient of temperature into temperature at that point. So this is the constant which doesn't change, or the constant part, I can say, and SP is also a constant, but it is just a coefficient of Tp. Remember, we are doing this for a volume surrounding point P. Okay, so this is E, this is W. So we're looking at how S bar would be in this volume. So it's a constant but coefficient of T and coefficient of Tp, and does not stand for S evaluated at Tp. Okay, it is no way it meant to imply that Sp is the value of S when we evaluate at Tp. Now there is a key idea here. When we assume this form, we are sort of presuming that this value of temperature Tp, remember that point P will have some temperature Tp, right? So we are presuming that Tp prevails over the entire control volume, over this control volume. When I say control volume, entire control volume, it means the control volume surrounding point P. Or in other words, it is actually a stepwise profile, the profile that we had discussed some time back. The first approximation which does not give a reasonable estimate of slope. So we have W, P, E. So we assume that there is a temperature which varies, right? So at point W there is a temperature which is spread in the control volume, and let's say this is E, this is W. Sorry. So we are sort of taking a stepwise profile in calculating this. Now, how do we know that it is a stepwise profile? So it is sort of like if you look at integral S dx between W and E, and we are writing this as S bar delta x. Okay, so the integral can be written as, if I assume that the temperature or the value of S can be written as a linear part, sorry, can be written as some function of temperature only, right? Because when we say that this is temperature is completely fixed, I mean we're taking the value of S based on some prevailing temperature, so T. So S basically sort of becomes just value of the, as a function of the value of as a function of temperature, right? And we are saying that we're trying to linearize, right? So what we get is, if I look at this integral now, so between E and W the phase length is delta x, A is a constant, and Tp becomes basically a constant along over the entire control volume. So we'll get A Tp delta x plus B delta x, and if I compare this with S bar, we said S bar is Sc plus Sp Tp delta and into delta x, because there's a delta x here. So this means Sc is the same as the constant part and Sp is A, right? So it basically is assuming this piecewise profile to calculate S bar. So this is T and this is X. So this is just in the same, I mean, so if you remember just a few minutes back, we spoke about this idea that the for a given, see, for calculating S bar we need not assume that T varies linearly. So that's what we are trying to emphasize here, that it does not have to be linear variation, it could even be piecewise variation. Okay, so now the discretization equation, once we've established that S bar could be written as Sc plus SpTp, now we can go back to the discretization equation in one dimensions, and what it would look like would be ApTp to be AeTe plus AwTw plus B, where now Ae is the same Ke by delta Xe, Aw is also Kw by delta Xw, and Ap would now be Ae plus Aw minus Sp delta X, because remember when we have that integral here, right, so we have an S bar delta X here, that is now going to be replaced by Sc plus SpTp. So Sp can basically go to the left hand side of the equation, right? So what we get is this variation, and B would now just be Sc delta X. Okay, so this brings us to the end of the first lecture in this series. Okay, in the next lecture we look at the basic rules that we have to work with to ensure physical realism and overall balance, which we have not looked at yet, and we'll also look at the two-dimensional formulation very soon and the transient analysis. Okay, thanks.